All right, so we're going to get started with logistic regression, and then we'll break for lunch in about 20 minutes. So logistic regression, we're going to talk about the form of the logistic regression, how to interpret the output of logistic regression, and most importantly, how to apply the syntax of a logistic regression on an example. There's a lot of math and there's a lot of mathematical theory that goes into logistic regression, most of which we will not be getting into. We are only going to be covering what you absolutely need to know to be able to use the logistic regression. However, after class, I will post links for the mathematically curious of you to go and learn about some of the advanced, and I mean, for me, I would say it's advanced math. Some of you might not think that, but I would say that it is advanced. So, logistic regression. If any of you have used logistic regression before or heard of it, where would you say that it belongs in this diagram? Is it a supervised or unsupervised? Is it a continuous or categorical response? So, supervised or unsupervised? Any ideas? Supervised, okay. So we're down to one of these two, and do you think it's for, by its name, do you think it's for continuous or classification? So I know that people have been following along in class if they say continuous because it has regression in its very name. But alas, that is misleading. It is for classification, not for continuous or regression problems, as we've been talking about. Why is that? Well, we're going to cover that today. Classification, supervised. What is logistic regression? It is a generalization of linear regression to classification problems. Realize this might not be super informative if you haven't taken linear regression before. We're going to be covering linear regression in the next class in great depth. But for those of you who do have a background, for those of you who don't have a background, it is a model used for making classification predictions. If you're familiar with linear regression uses a set of input variables to predict a continuous response variable. In logistic regression, use a set of input variables to predict probabilities of class membership. This is one of the best features of logistic regression. It is not only good for predicting class membership, but it is also good for predicting the probabilities of class membership. Not all classification models are good at that, but logistic regression is, and we'll see why. Class membership is not always binary, but that's what we're going to be using in this class. I would say that logistic regression is conventionally thought of as a good for binary problems, and that other models are better for problems where you have more than binary class membership. If you have a trichotomous variable or more, then I think that other models would be better for that. But the logistic regression, as I said, predicts probabilities, which can then be mapped to class membership. So, let's talk about the form of logistic regression. In linear regression, a single linear regression takes this form of an intercept beta naught plus beta 1 times x. We'll talk more about why that is in the next class, but it's capturing a linear relationship, also known as y equals a plus mx plus c. I think that's the typical way of saying it. Algebra, just a formula for a straight line. And it's different in logistic regression, and it takes on the following form. E to the beta naught plus beta 1x over 1 plus e to the beta naught plus beta 1x. And that gives you the probability of class membership in a particular class given x. Math speak here, y equals 1 given x. Okay? Now, what is E? Can anyone tell me what E is? In this case. What is E? E. What's that? 2.7 something? Is there a name for it? Natural log? Okay. It's one of probably the five most important numbers in the history of math. Which, by the way, today is Pi Day. Happy Pi Day. That's one of the most important numbers in the history of math. 0, 1, pi, e, and one other one. Probably some of the most important. E is just Euler's number. It's 2.7 something. I don't know it past 2.7. Has some very special properties, but for the time being, we'll just define it as this function, and we will move on to some of these special properties momentarily. So in a lot of textbooks, you'll see the probability annotated as the pi symbol, which I know might be a little confusing, but I include it here because the pi symbol is used in textbooks that I consulted when creating this material. So, pop quiz for the next 10 minutes, and then we break for lunch. In your code, in the folder, you'll see a file labeled, I think it's just called Logistic. I think it's just called Logistic Exercise. Yeah, Logistic Regression Exercise. Go ahead and open that up. And once you open it up, the exercise is to plot, just using this information that I've given you. This is the form of the logistic function. Go ahead and plot xy coordinates. Y is the probability of class membership. X is just x. What the shape of this is for an arbitrary beta. And I'll just give you beta values so that we all sort of get the same plot. Let's say beta naught is equal to 0, and beta 1 is equal to 0.5. So go ahead and take the next image. And for this exercise, we're going to do something we haven't done before. We're going to pair up k nearest neighbors. Is k is equal to 2. So pair up your nearest neighbor. So you2 and you2 and then you2 and you2. Maybe Jody and Tom can pair up. And then, let's see, you2 and then you2 and then 10 minutes. All right, so we'll get started back up again. What I wanted to do now is just to show you the way that I wrote this solution to the quiz. So if you're stuck, you feel free to copy this down. So I just created a linspace, an array of numbers. I specified the starting point, the end point, as negative 20 to 20, and I wanted 1,000 data points. Sorted that in my x variable. Then I created a list of beta values, 0 and 0.5. And then I created the function, and I used the exponential function from the NumPy package.
So it's going to know the sign. It's still 0 and 1.
What's that?
It's going to know because your array is 0, 1, 2. But you put beta equals 0, you didn't have to sign them separately.
Hang on 1 second. Sorry, say it one more time.
Beta.
Uh-huh.
You can have it assigned separately.
I don't have. You don't have to. You can assign them separately if you want to. It's up to you. So here I've got a list of beta values, and then my numerator is just the exponent, raising to the e, beta 0 plus beta 1 times x. And because this is a NumPy array, this beta 1 value will multiply across all elements in my array. Yes? Load up a little more? Sure. Okay? Okay. And then the denominator is 1 plus e to the beta naught plus beta 1 times x. Exact same as the numerator, except you have the addition of the 1. And that is it. So why don't you go ahead and take 5 minutes, and with this help, try to go ahead and plot the shape of this function. All right, and we're back. Let's plot this sucker. So we've got imported the matplotlib.pyplot is a plotting library that we haven't covered explicitly in class. The plots that were generated in your pandas homework used this plotting library explicitly. We've been using it implicitly in the sense that we've been using the pandas plotting functionality, which is essentially a wrapper or a convenience function around the matplotlib library, which is the standard library in Python. So if you didn't do the homework, this might have looked a little bit new to you, but it's very simple. It's as simple as calling the plot method and then specifying the two variables you want to plot one against the other. And here you can see that I'm just specifying my x variable, which is based on the linspace array, and then my y variable, which is just based on the function that I've just defined. And I include some other parameters in here that are optional, but I think we've talked about them. Just the adjusting the way the line is going to look. And I didn't define this. So let me just go ahead and plot this, and then I'll just format it a little bit. These next 4 lines of code that I'm running just truncate the x and the y axis. They also add in some reference lines and label the y and x axis. I'll post this after class, and you can take a look at it. So this is what the resulting graph looks like, plotting from -20 to +20. How many of you got this? A handful of you? Okay, great. So let's talk. I want to talk about this shape and some of the features of this shape. So I'm going back to the slides. So the function is this S shape, also known as a sigmoid shape, and it is bounded on the y-axis by 0 and 1, which makes sense given that we're trying to predict the probability of something occurring or not occurring. What jumps out at you when you look at this shape and think about the kind of problem we're trying to solve, predicting the probability of class membership? What is it about this shape that makes it a sensible shape for a function trying to predict the probability of something occurring? Why an S shape? Okay. So in this case, the y-intercept is at x equals 0. That is true. Yeah, that may or may not be the case, if we were to use different beta values. And we'll talk in a moment about how the beta values affect the shape of this. But just looking at the shape, what jumps out at you? Converges to 1, okay. So it converges to 1 and 0, and then extreme values. So that makes sense, right? Because probabilities are never going to be more than 1 or less than 0. A probability of 1.2 doesn't make sense. Well, certain you can be is 100%. No more certain than that. Okay. Another thing that's interesting about it is that it has a gradual increase, but the slope changes. The marginal increase in probability corresponding to an increase or a decrease in x values. To get an increase in probability of 1 or 0, as you get sort of approach the extreme ends of your input range, you have to increase your input marginally a lot higher to get a marginal increase in productivity on the extreme values versus on these central values where just a small change will increase the probability. There's a lot that can be said about this shape. It turns out it's a very convenient shape for this particular problem. To help get a little bit more understanding or intuition behind what this shape is, I want to talk about how the shape is affected by the beta values. The beta values are not something you would programmatically define. These would be the output of the model that you build. But how to interpret these and what kind of impact do they have on the shape? So if you change the beta naught value, the intercept value, in a very similar way to the way it would change a linear regression, it also changes this logistic regression. It shifts in other words, it shifts the y-intercept either up or down. As you decrease your beta naught value, you decrease your y-intercept. So this beta naught value is -2, and so you can see that's much lower. And the black beta naught value is 3, and so you can see that's much higher than before. So depending on where your beta naught value is, that's going to affect where your y-intercept is. The second thing, the beta 1 value. The beta 1 value is the value you're multiplying by your input variable. Changing the beta 1 value changes the slope of your S-curve. And so a positive beta 1 value will result in this kind of S shape. And a negative will reverse this shape. And as you increase the magnitude, that will increase the slope here in the middle of the shape. So that's just some very, very basic information about the logistic regression. How do we actually interpret the output of a logistic regression? So in order to do this, we're going to need to take a step back for a moment and talk about the difference between probability and odds. Okay? And the reason why we're talking about probability and odds is because the output is going to give something that's interpreted in reference to the odds. And the derivation is also something that's derived using the concept of odds. So the odds of an event are given by the ratio of the probability of an event and its complement. What does that mean? So let's say I have my chances of admission to graduate school are 33, are let's say 10%. I have a 10% chance of getting into graduate school. This is a really elite graduate school. What would my odds, what would be my probability of admission? All other things being equal, let's just say a random distribution, my probability of getting into graduate school, this particular graduate school, would be 10%. Okay? And what would be the odds of that in that case? So it's the probability, which is 10%, divided by the complement. So the complement of 10% would be 90%. Either I get in or I don't get in. So in that case, the odds would be 1 or 10% over 90%, or 1 over 9. So the odds of me getting in would be 1 over 9. In other words, for every 9 programs that I apply to, I get into 1. Okay? So this is the formula here. It's the probability divided by 1 minus the probability.
For every 9, wait, you said for every, if the probability is 10%, the odds would be 9.
1 to 9 or 9 to 1, depending on what you're talking about.
So for every 10, the odds, or the chance, sorry, right?
For every 9 that I apply to, I would get into 1.
For every 9 you're rejected from, you get into 1.
Yes.
So apply to 10.
Sorry. Yeah, that's correct. For every 9 that I get rejected from, I'll get into 1.
Okay.
So, what is the range that the odds could take upon? Zero to infinity. Yes. So probability is 0 to 1, and odds are 0 to infinity, because the probability could be 0, or the probability could be 1, in which case, or approaching 1, in which case this would just be 1 over something that is very, very small, or 1 over 0. So here's just here's an example similar to the one I just shared. Let's say you're trying to determine whether a customer will convert or not. The customer's conversion rate is 33.33%. What are the odds that a customer will convert? So using this formula here, the odds. What are the odds that a customer will convert? So just take a minute and just maybe write this out, or just do it in your head, and then I'll show you the answer. Given the previous example I just shared, this should be rather straightforward. The odds that a customer will convert are the probability of conversion, just given in this problem statement to be 33%, divided by the probability of the complement of that event. And so for every 2 customers that do not convert, you should have 1 customer that does convert. Any questions about this so far?
Why do we use the term odds? This just seems like purposely.
So are you asking the question, like, why use the term odds just in general, or like why am I going for odds right now in class?
I guess just in general, do we use odds in a certain, I guess I'll find out.
Yeah. So just this part of the class, it's just go with me for a moment on this, and I'm leading to something. Here's the part where I'm asking you to take a step of faith with me, and I'll tell you why we're doing this in just a moment. What would happen if we were to take the odds of the logistic function? And remember, the logistic function is giving us the probability of class membership. So the odds of the logistic function. Here, I'm going to show you a little bit of math, So if your eyes glaze over, that's okay. You don't need to follow this. But here we have the probability on the numerator. There's the logistic function divided by 1 minus the probability on the denominator. This is just taking the odds of the logistic function. If you multiply this out and simplify it, and you want to know the details of this, I'm happy to go through with you. You get something very nice. E to the beta naught plus beta 1 x. So it simplifies quite nicely. And so we're comparing, so this is the odds of the logistic function, and it's a little bit cleaner, a little bit simpler than the actual logistic function itself. Okay? The reason why I'm going down this path is because I want you to have a little bit of the intuition behind how the logistic function is created, how it's derived. Okay? We're not going to go through everything. We're going to go through a little bit of it. If we were to take the logarithm of the odds, we return a linear equation. So can anybody define for me what a logarithm is? And here, this is the natural logarithm. But just in general, anybody, maybe Heather, would you like to define for us what a logarithm is?
The inverse of the exponential.
Okay.
So that if you apply log of e, you get log of e gives x, e to the log of x.
Okay. Anyone else want to take a stab at it? Pretty good definition. The log of a number, so logs all have bases. The log with respect to a certain base of a number is the exponent that you have to raise that base to get that number. Okay, so let me give a trivial example. I still can't decide which way or people see the best, but let's go with this one. So log, and logs can have different bases. The common one is log base 10. So log base 10 of 1,000 is equal to 3. Because 3 is the number that you raise 10 to get 1,000. Okay? And then you can have different kinds of logs. So log base 10 is a very common one, and log base e, also known as the natural logarithm, to, let's say, e to the 5. What would this return? 5. So that's what a logarithm is. What we just went through is something called the Logit transformation, I believe. Getting the name right? Yeah, the Logit transformation. And this relationship is key because it's key to understanding. This is what will be returned. We'll get these beta values. And this is the way, this has to do with the way that the solution for the beta values are derived. So the beta values are derived actually using a technique, a very common technique in statistics called maximum likelihood estimation. So given the data that we see, what values of beta naught and beta 1 are most likely given the distribution of data that we see? And here's where I'm getting into just sort of pointing in the direction of some of that advanced math that goes into this. And due to the complexity of the form of the function, the beta values are estimated using an iterative procedure. There's different iterative procedures that can be used to estimate these beta values. A common one that you'll hear of is something called, I think one of the more common ones is Newton-Raphson, if that rings any bells for some of you. I'm going to include a link or send a link in Slack to a technical derivation of this. It includes calculus, it includes matrix, algebra, linear algebra. And so for that reason, I'm not taking class time to go over that. But for those of you who are curious, you can go into that. So this relationship is how the beta values are estimated. So drawing the analogy, comparing back to the linear regression, in linear regression, beta 1 represents the change in the response variable for a unit change in x. In logistic regression, beta 1 represents the change in the log odds for a unit change of x. So remember again, this is just the log odds. We have the odds and we have the log odds. Okay? Now, at this point, I'll just like to make the note, this is why it's called logistic regression. Because you're solving this equation that is the same form as a linear regression, but the response variable is not y, it's the log of the odds. So logistic regression, this is where the name comes from. The corollary of this is that e to the beta 1 gives us the change in the odds for a unit change in x. I'll skip through that because we haven't talked about significance yet. We'll talk through that. I'll just make a mention here. The package we're using is not going to estimate p-values for these coefficients, but p-values are readily accessible through other packages for logistic regression. And what the p-value tells you, as we sort of hinted at earlier, is whether or not a certain coefficient is significant or not. There's another package in Python that does this called stats models. We won't be using stats models. We'll be using scikit-learn just for continuity purposes. But if you're interested in that, I can definitely help you with implementing that if you would like to use it. So for the next half an hour to 45 minutes, I'm going to ask you, if you're not familiar with this, I'm going to ask you to put your thinking cap on and go with me on a little ride. This is going to be this is going to be probably some of the more complex material we cover in this course. At least it was for me. So, question is, once you do a linear regression, you get an output, and part of your output are beta values associated with coefficients. The question then is, how do we interpret those beta values? Okay? What do we do with that? Obviously, we know how to plug it into an equation and run the results, but how do we interpret it? So, suppose we were interested in mobile purchasing behavior, similar to before. Let y be a class label denoting purchase, no purchase, and let x be whether the phone was an iPhone. Okay? We perform a logistic regression, we get a beta 1 value of 0.693. Okay? What does that value mean? So in this case, 0.693 corresponds to a unit increase in the log odds, as we said before. But log odds, like, what does that even really mean? That's sort of difficult. What does it mean in terms of the odds? The odds ratio is the exponent of 0.693 equals 2. I purposely picked an easy number there. Which means that, and it's a positive number, which means that if the phone is an iPhone, the odds of purchase are twice as high as if the phone is not an iPhone. It's either an iPhone or it's not an iPhone. If it is an iPhone, then the likelihood of purchase is twice as high. So this is a very brief example. We're going to run through an example in class with some real data, and we're going to come back to this point. I think this is probably the hardest. Part of understanding logistic regression is understanding and interpreting these coefficients. So we're going to come back to this. in detail during our example. So just to sort of extrapolate this point, we just did the case where we have a single x variable, but the same approach, interpretation, everything can be applied to multiple x variables. It doesn't require just a single x variable. So I mentioned earlier this is called the logistic function. It's also sometimes called the logit function. I'm sorry. The logistic function and the logit function. The logit function just being the log of the odds. Oh, the logit function just being the logarithmic transformation. So what I wanted to do now is really focus on what I think is the hardest part of understanding the logistic function. But to do that, I want to get into the data and actually explore a new data set that we haven't looked at yet. So this data set contains 10,000 records associated with credit card accounts. And there are 4 fields in these credit card accounts. There's whether or not the person defaulted, which is a binary variable. There's whether the person was a student or not. Their the current balance on their credit card, and how much annual income this particular credit card owner makes. So that is where we will switch over to our Python code. And you'll see in the exercise script, there are a series of steps that are outlined. And let me go ahead and pull that up. Okay, so there's 2 parts to this. What I want you to do now is, in the same groups as before, go through the part 1 steps, which are the exploration steps. And so this is meant to simulate something you might be doing currently or have already done with your project data. So you're going to read in the data. You're going to split the data into train and test sets. You're going to create a histogram of all of the variables. You're going to create a scatter plot of 2 of the continuous variables, income versus balance, and you're going to color the defaults with a different color and symbol. And you're going to try to make some inferences based off of this exploratory analysis. So go ahead and let's take the next 20 minutes or so and split up into the same groups as you were before and go ahead and get started on this. Any questions about any of that? Okay, perfect. All right, we are back. Guys excited? Finish out strong? All right. So I'll just walk through the solutions to part 1 briefly, and then we'll all go through part 2 together. So let's get right into it. So I'm going to set my working directory, and I'm going to read in the data. My default data set, I'm storing this in a different folder that I haven't uploaded to GitHub yet, but I'll upload this after the class, and I just put a copy of the data in that folder as well. So I read it in, and I looked at the first 5 rows, and converted everything to numeric. The way that I would do this, and the way that I would recommend doing this, would be to use the np.where command. This is a very useful command. And what it does is it looks at each row in the series that you pass it, and it evaluates whether the logical condition is met. And if it is met, it returns the first option. If it's not met, it returns the second option. So here I'm saying if the student is equal to yes, then place 1. If not, place 0. Can you guys in the back see okay? Yeah? Okay. This is not the only way to do it. I include in the comment another way of doing it. I won't go over that. So split the data into test sets. First of all, I'm going to split between my x and my y variable. I'm going to say, here's my x and my y variable. So let me run this command. And actually, you know what? Let me run that command. Run x and y, and then I'm going to split up into my training and test set just as before in the iris Canon example. X train, X test, Y train, Y test. All right. Now what I'm going to do is I'm going to convert back to a data frame. And really the only reason I'm doing this is for convenience, so that I can have my labels back in my data. What returns from the train test split is NumPy arrays, unlabeled data arrays. Even if you pass it a labeled data frame, it will return an unlabeled data set. So I'm just going to go ahead and convert this back so that I can have a nice label for each column in my data set. Then I'm going to create a histogram of all my variables. This can be accomplished just by running the hist method on the data frame. You can see all the different values there. This is obviously not the only way to get a histogram of all the variables. You could do things that are much more complex than that. But this is one of the nice features, again, about pandas plotting, is that if it has it implemented, it's probably pretty easy to do. If it's hard to do, then it probably hasn't been implemented yet, and you're better off using something else. But this is very nice. So you can tell right away, you have a rather normal shaped, close to normal shaped distribution for income. The balance distribution is not normal, it's skewed right. For default, you've got only two values, 0 and 1, as you'd expect. Same thing for the student. Yeah, if you had a converted student, you would not see the student variable there.
What's the
You just, the data frame dot hist, and any of the continuous variables in there will pop up in histogram.
So we were supposed to do that on the train set for data, and not, or on the.
So, good question. I did that just on the training data set. Why did I do that? Well, I'm sort of developing ideas about what I want to measure, what I want to model, and the same logic of only fitting the model on the training data set because you want it to generalize the test data set similarly applies to the data exploration phase where you are visualizing the data. Because visualization and modeling are two forms of exploring data, identifying relationships in data. And so, very strictly speaking, I probably would just explore the training data set, but other people might disagree with me on that, and it's more of a personal preference. So the student, I don't think. So how could you tell if there was any missing values in your data set? Well, you would type in train.isNull.sum. And you could look at, for each column, whether missing values are present. In this case, there are no missing values.
I thought you meant from the graph. We ran the same line if we only get 3 or 4 graphs. Just do that.
Oh, sorry. So if the student is not an integer or a float, it will not show up in the graph. Float is just with decimals.
Would be the trend.student.hist shown in the graph.
Oh, really?
Yeah.
Huh. What happens if you do the dataset.dtypes? Is a student an int or is it an object?
It's an object.
It's an object. Okay, so here's what's happening. the way you converted it, you probably did something where you converted one at a time, and so to maintain the continuity of the data type, it kept everything as a string. So even so, you see ones and zeros, it's really strings. Versus doing it all at the same time, it'll interpret correctly that you want to place integers in. That being said, you can convert the type of any data frame just by the column and then dot as type, and then inside parentheses int or whatever you want. So you can give that a try. I think that works, but tell me if I'm wrong. Create a plot, scatter plot of income versus balance. So I'm going to use the pandas plot method, and kind equals scatter, which I believe I saw many of you creating this plot. It's not terribly informative in and of itself. There's no pairwise relationship. There appears to be no strong groupings in the data, although maybe you could say there appears to be less density here than up here and here. So maybe these are two different groups of people. Like college students, and students down here, and maybe non-students up here. I don't know. I haven't actually plotted that. So you could see if you could infer what those two different groups are, if you'd like to. But what we're going to do now is just try to plot the defaults and the non-defaults over top of each other on the same graph to see if we can find any general relationships about this. So the way that I did this, which is not the only way of doing it, but it was the most intuitive to me after trying lots of different ways, was to create two separate data frames, one of the default data and one of the non-default data. So here I'm just using basic logical filtering. And what I'm going to do, this is probably the least, this is the most difficult part of the full first exercise, creating these overlaying scatter plots, because and it's not your fault. Okay, this is an area where it's a weakness of pandas, and so it's not your fault if you found this to be difficult. What you may have thought of doing here was doing a where command, and where this is true, color this, and where it's not true, color that, and a similar kind of thing with symbols. It turns out in pandas, that only works for colors, and it doesn't work for symbols. I don't know why that's the case, but that has not been implemented yet in pandas. We can only hope that in the future that will be implemented in pandas. But one of the things you'll run into is sometimes things just don't behave exactly the way you want them to behave. So there's value in being able to know, okay, what are multiple ways of doing the same thing? What's a different way of doing the same thing? And so that's really the reasoning behind creating the two different data sets here. It's almost like a hack, if you will, for a feature that, in my opinion, should really be implemented in pandas. The other thing that I noticed is that if you use the pandas scatter plotting, you plot one after the other, at least on mine, with my default settings, they would just come up as two separate plots. And so what I did here is I actually used just the PyPlot module, which was used in the homework assignment to create the two different scatter plots. But that being said, there may be a way to overlay two plots using the pandas plotting as well. Here I'm just using the PyPlot module, and I'll scroll up so you can see that. This is the matplotlib.pyplot, and this is also the command used in the homework assignment. So if you followed along with that, that is one place where you could have referenced from. And I'm specifying the parameters here, the x variable and the y variable, and the alpha values, the marker values, and then I'm just creating a legend using the .legend method. Okay, so I'm going to run this whole line of code, and this is what you get. So. Did I write? No, I didn't write commands for the x-axis. I could have labeled x-axis. So this is the balance variable, This is the income variable. Even if you didn't know the order of operations, you could sort of income from 0 to 80,000 makes more sense than the balance from 0 to 80,000. At least I hope so. So with that being said, you know, what would you infer from looking at this plot in terms of the nature of you know, the relationship, the effect of these continuous variables on the variable I'm trying to predict? What would you infer from looking at this plot?
A high balance indicates like default.
Yes. How about income? Would you say a higher income or a lower income indicates?
No.
Nope. Yep, exactly right.
What's on the X again?
X is balance. So you increase your balance, likelihood of default increases. As you increase your income, there doesn't appear to be a relationship here.
Yeah, I was gonna say. It's opposite.
Oh, I'm sorry. I got the legend wrong. Thank you for noticing that. If you guys notice anything like that, please let me know. My apologies. There we go. much better. No, good. Okay. Hey, if you guys correct me, then you guys could look smart. So that's awesome. Win-win situation. There we go. Make more sense? Okay. 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 So now let's go ahead and run our logistic regression. Okay, we're going to do this together because we're running short on time. But you'll find that a lot of this process is going to look very similar to what we did with KNN because we're using the same package for fitting the data. Yes.
Can you remind me why? Do we know that the logistic regression is a good one for this set? Because it's just two. It's just y and x and y.
Okay, so yes and no. Yes and no. Yes, because we're looking at a binary response. We know that logistic regression maps to is a classification model for a binary response. No, because this is only our second modeling technique, KNN and logistic. Could we run a KNN on this? Absolutely. We can compare the KNN's results with logistic results. This is only our second model covering past that. Yep. Okay. So I'm going to call this. I'm going to call my model, and this logistic regression. You'll see where I import this. From sklearn.linear model, import logistic regression. Okay. Let's see how you import it. And then I'm going to instantiate my logistic regression with just the default parameters here. And then I'm going to fit the logistic regression on the X and Y data, training data. And then from balance, you can see there's different attributes of this fitted logistic regression. The one that I'm interested in looking at are the coefficients. So what are the coefficients? All right. Wait a second. Balance.fits. Balance.coefficients. So the coefficients are just any of the beta values that are being multiplied by the input values. In this case, we're only doing a single input variable, so we only have one coefficient. I'm going to take this coefficient, I'm going to store it in beta 1, and you can see at the value of 0.004297. I can also do a similar thing with the intercept. I'll do that. And then to understand the relationship of the interpretation of this, you commonly will take the exponent of it. And so when you take the exponent of it, then you understand the relationship between the coefficient and the change in odds. The beta values by themselves represent the change in the log odds, which are not as commonly used. I want to come back to the coefficients and talk more about that if we have time. but for the time being, let's just continue going through the workflow, and in a similar way that we did with the KNN model. So if we were to predict the probability, so let's just say we've got this model, and we want to predict the probability of default for two different people. One person with a balance of $1,700 and one person with a balance of $2,500. Okay? So the way that it works is that you call the fitted model, you call the predict proba, if you want to predict the probabilities, the predict proba method, and then you can pass it a data frame with the balance label. And so this might look a little clunky, but what it is actually very simple. It's just a data frame, a labeled data frame called balance with two values in it. And this is what I'm passing to my predict function. The reason why I'm giving it actually, I'm not sure. I think the label is necessary because it's going to be looking for a label because I used a label to fit it, but the balance label actually might not be necessary in this case. I'll test that in just a moment. So once you get this, you get a 2x2 array, and what it shows is the probability in the first row for the first observation. This is the probability that it won't default, and this is the probability it will default. And then for the second observation here. So if you were to make a prediction based off of these probabilities, the first observation would probably be no default, and the second observation would be that there would be a default, which corresponds to our intuition from looking at the scatter plot. As you increase your balance, the second one had a higher balance, you have a higher likelihood of defaulting. And then you can also just get the class itself by just the predict method. And you can see it. The first data point predict class is no, 0, no default. And the second predict value is 1, yes, default. So there's two columns here because there's two classes. These are the probabilities of each class. These are just the components of each other. Any questions about that? Okay.
So is the predictor, is it just like 51% goes one way?
Good question. Really good question. Where's the cutoff?
Yeah.
I believe the default cutoff is 50%. But I would look at the documentation to double check that, but that makes sense.
Yeah.
Default cutoff would be 50%. That's something that you could change. Great point. Okay, so we've only got 40 minutes left, and I want to talk about what these beta values mean a little bit more. You know what? I created some code that tries to drive home the point of the difference between probability and odds, but graphically. Explain it graphically. Plotting both values with this example that we just created. So I will leave this as an exercise for your own exploration if you would like to explore this further. But in the interest of time, we are going to have to move on. I'll just show you what it looks like. Okay. So this is just a plot that shows On the bottom plot, it shows the log odds, which, as you remember, is just a linear function with respect to x, unbounded on either side. And this is using the same example we just created. Okay. The second plot shows the odds, which is bounded. It's bounded by 0 on the lower end, but it's unbounded on the upper end. It goes to infinity. And then the last plot is the one that we ultimately care about, the probability, okay, which is given by the sigmoid function that we went over earlier. Now, a very, very logical question you might ask is, how do you interpret these beta coefficients? As I said earlier, the beta 1 value for the log odds corresponds to a unit increase in whatever you're trying to predict. So here I've plotted 2 points. 1,700, a person with a balance of 1,700, and a person with a balance of 2,500, and plotted those points on each function, and you can see that there's a linear relationship, and if you multiply out the beta coefficients, you'll see as well. There's a linear relationship. You just multiply the beta coefficient, 0.0047 or whatever it was, times this value to get this value. Here, it's a little bit more subtle. You multiply the original value by e raised to the beta value times the increase, which is 800, to get this value. And here, there is really no way of mapping, generally speaking, what a beta value corresponds to in the probability region, because it depends on where your starting point is. That's I know that's sort of complex. If you're curious, though, go back and sort of play around with this data. Here's what I would say. If you want to go deeper into this, I included a link to a post that talks about E, and it explains what E is, Euler's number, and it gives a very intuitive explanation for E and a lot of these concepts that we're talking about, just for the sake of time going over pretty quickly. If you're more interested in learning about this stuff and curious about it, I would highly recommend that you check that post out, which I included in the references section. For now, I want to move on and bring this discussion to a close with coming back to the topic of accuracy and how you measure model accuracy. So let's go ahead and make predictions. Let's evaluate our model using the way we evaluated the model with the KNN. Okay, so we're going to make a prediction for the class just by passing the test balance variable into the predict method. And so now we have class membership here, which is a bunch of zeros and ones. And now we can measure the accuracy of this prediction. We can do it with score. I wrote out the code here, which is just another way of saying what the score is, but you'll see why I wrote it out in just a moment. I'm just saying whatever the predicted class is equal to the default class, this will return true. Sum up all those true values and divide through by my total number of predictions. So out of all of my predictions, how many did I get right? 97.5, 97.6. Tell me what you guys think. Do you think it's a good classifier or a bad one? Just if you got hand wavy, fat finger, good or bad? Good? 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 Any bads? Any unsures? Jody's unsure. Okay. So let's look at something in machine learning that is called specificity. Okay? What this means in this case is for those who didn't default, how many did it predict correctly? So going back to, we'll define another data frame. It's just people who didn't default. And we're going to calculate the specificity the same as before, except we're just using the people who didn't default. Wow, 99%. Good. Really good. Okay, I'm feeling good about this one, guys. I'm ready to call it a day. Let's just check one other metric, the sensitivity. For those, and this is we'll come back to these terms, but sensitivity in this case means for those who did default, how many did it predict correctly? This is like almost like the complement of the previous one. So same thing as before. Boo! 27% accuracy. How in the heck did we miss this? Any ideas?
There are much less that defaulted, so it may have screwed up most of those, but in regards to the majority of data points, it got most of them right. Is that what it is?
Did you guys hear what Matthew said? Yeah, so if you remember back to the histogram, I don't have it up anymore. If you remember back to the histogram, there was a lot more people that did not default than people who did default. So it's a very common problem called class imbalance, where you have a different number of observations in each class. And so if you just look at the total accuracy, it's mostly affected by the people who didn't default, because all trues and falses are evaluated equally in that case. And so if you don't look at it class by class, you miss out on telling whether your model is really that good or not. When you have class imbalance, at least. Here's another thing to consider. What would happen if I, instead of doing the predict class, I did predict proba, and then I took the predict the probabilities instead of the classes. So let's call this pred proba, and what do we get here? This is a probability of 0 to 1. Let me just merge this. Predict proba, and we defined our own threshold. So we didn't define 0.5, we defined our own threshold. So if we define 0.5, we'll get the exact same rate. And we said predict class 2 is greater than or equal to 0.5, or greater than or equal to 0.7. Here, predict. Oh, sorry. There we go. True or false. So here we have something similar to before, except we're defining our own threshold. Okay? And we'll say it's 0.7. Would we get different results? Well, let's substitute in what we did before. Pred class 2, and look at the results. 97.1. What did we have before? It was 97.6. Okay. Well, let's try here. Pretty similar as before. Let's try here again. Sensitivity much lower. So it really it really it raises two questions, or it drives home two points, I suppose. The first is that your class imbalance will affect the way your model accuracy is interpreted, and you should look at the accuracy for both classes they are predicting. The second is that your accuracy metrics will be, if you look at just the classification rates, will be affected by the threshold you choose for mapping the probabilities to the class labels. Okay. We have 30 minutes. So in 30 minutes, I'm going to try to get started on the rest of the model evaluation metrics for the classification piece and talk about some ways that are more advanced than what we've just talked about for accounting for these 2 points that we just talked about. Okay? So go ahead and open up the model evaluation metrics presentation. Model evaluation metrics. So there's 3 model evaluation metrics we're going to go over. I'm going to skip over the root mean squared error, and we're going to cover that next class for the linear regression. And I'm going to say we're going to focus on something called the confusion matrix and the ROC curve. So I'm going to skip over this and come back to it. The confusion matrix is a table that's used to describe the performance of the classifier, and it can be interpreted as follows. On the x-axis, you have your actual values, and on the y-axis, you have your predicted values. And the diagonal shows you the correctly classified observations, and the opposite diagonal shows you the values that are not on this diagonal show you what you did not get correct. So this is a tool that can be used for more than just binary classification problems, but that's what we're going to use for this example. So in this example, it changes up the analogy slightly, but you can still think of it as actual no referring to people who did not default, actual yes referring to people who did default. So in this example, we would say 100 people actually defaulted, and we predicted they would actually default. Whereas 5 people actually defaulted, and we predicted no, they would not default. This gives you a little more detailed picture of the performance of your classification. There's a lot of terminology that goes into evaluating a model, but all of it can be traced back to this confusion matrix. And so what I'm going to do here is list out some of the terms, and I would not expect you to memorize this, especially if you haven't heard of a lot of these terms before, partially because there can be often multiple terms describing the same thing. So instead, I'll just highlight a couple things and leave this for you as reference to refer back to in the future. So the misclassification rate is the complement of the classification rate, which is just regardless of what class you're predicting, how often are you wrong out of how many predictions you're making, how many data points you have, or the classification rate is just how many times you're right out of how many data points you have. That's the score method we were using earlier. That's the accuracy that I showed you, how you would program it out. This is very, very, very class agnostic. This the 3 things maybe I would leave you with would be the sensitivity, which is when your actual value is positive. So in this case, how often is your prediction correct? So in this case, you'd have 100 predicted correct out of 100 plus 5. So sensitivity. How sensitive is it to what the actual positive signal you're looking for is? How sensitive is it to picking up on the defaults, whether or not someone's going to default? How sensitive is it to whether or not somebody actually has cancer? This is also known as the true positive rate or recall. Again, multiple terms for the same thing. It's confusing. Don't expect you to memorize this. Specificity. When the actual value is negative, how often is the prediction correct? So in this case, how many values do you have that are actually negative? 60. And how many did you actually get correct? 50. 50 out of 60. Specificity, I don't have really a good intuition for like remembering specificity. I just remember sensitivity, and then specificity is the other one. So sensitivity is also known as the true positive rate, the false positive rate. When the actual value is negative, how often is the prediction wrong? So when the actual value is positive, how often is the prediction correct? That's the true positive rate. When the actual value is negative, how often is the prediction wrong? Is the false positive rate. So I'll just leave you with that for right now to refer back to. So yeah, we'll just leave it at that for right now, because I want to spend the rest of our time going through the ROC curve. Now, if it were up to me personally, this is just a personal bias, I might not actually go through the ROC curve. The reason why I'm going through the ROC curve, because I don't use it a lot personally, but there is value in it, and you will see it a lot. Just in literature, you read about these methods, and there are some unique aspects of the ROC curve that give it an advantage over your typical sensitivity, specificity. So let me just give you briefly the motivation for it, because it's sort of complex. It takes a while to digest. The motivation for the ROC curve is that, one, it's not sensitive to class. It's not biased by class imbalance. So it takes into account when you have a class imbalance difference. It gives you one number, and it's not affected by class imbalance. Two, it is not based off of a threshold value that you define. So let me say that again. It takes into account class imbalance, and it's not based off of an arbitrary threshold value. That is the motivation for learning ROC curve. Okay? That being said, I'm going to fly through this and show you what it does briefly. So the way an ROC curve looks is that you have an x-axis, which is the false positive rate, and a y-axis, that is the true positive rate. What is the false positive rate and true positive rate? To use another example, the true positive rate is when an actual email is spam, how often is it predicted to be spam? Going back to the default rate, when an actual person defaults, how often is it predicted to default? When an actual value, false positive rate, when an actual value is ham or no default, how often is the prediction wrong? So that being said, we have a sample data set here of 8 observations. And we've trained a logistic regression model on it. And it's made these predictions about the probability that it's spam. Okay? So here, 99% probability it's spam. Here, 2% probability it's spam. And then we also have the true labels, whether these really were spam or ham. And this is actually a problem we're going to solve in class. We're going to create a model to make these predictions on a real data set. So that being said, how good is this model? Using the ROC curve. Here is the way the ROC curve works. The ROC curve picks multiple values for cutoffs, for thresholds, and then it evaluates the true positive rate and the false positive rate, and then it plots them against each other. The single value that comes out of the ROC matrix, ROC curve, is something called the AUC, the area under the curve. ROC, I forgot to mention this, stands for receiver operating characteristic. AUC is the number that you get out of this. So let's go ahead and let's go through this together. So when you have a cutoff value of 0, what is your true positive rate going to be? So when the actual value is spam, and so after a 0, you're basically saying everything is spam. That's what the cutoff means. Predicting everything to be spam. When the actual value is spam, how often is the prediction correct? We're predicting everything to be spam. When the actual value is spam, 1, 2, 3, 4, how often is it correct? 100%. 100%. Because remember, our threshold, our cutoff is 0. Okay? 100%. Everyone follow that? 100% predict true positive rate. Yeah? Okay. So when the actual value is ham, how often is the prediction wrong? So we got 4 hams. This one's going to be labeled as spam. That's going to be wrong. Spam, spam, and spam. All 4 are wrong. We've got 4 hams, and all 4 are wrong. 100%. Let's, we won't go through all these. Let's go to another one. 0.25. True positive rate. We've got spams here, here, and here. How many of those are we can actually predict correctly? 100%. Correct. Okay. So 25%, so below 25%, we're going to predict is, so when the actual value is ham, remember everything below 25% is going to be predicted to be ham. How often is our prediction going to be wrong? 25%. We're going to predict this guy wrong. Because this guy's ham, but he's above our threshold. So we're going to predict this guy to be spam, when in fact it's really ham. This guy's going to be wrong. These guys are going to be right. 25%. I won't go through all the examples, but this chart just illustrates a couple of points. What you do when you see a receiver operating characteristic is a plot of a bunch of points. Okay, so it's choosing different threshold values. This is why I say it's not tied to one particular threshold value, because you're choosing multiple threshold values. Okay, and you are evaluating them together as a whole. Okay. What this graph would have looked like, I didn't have time to put it in there, is it would have started over here. Remember, they were both 100%, and they would go something like this. And you want it to be the larger the area under the curve, the larger the accuracy. So I know we flew through that. Let me pause and ask if there's any questions about that, because we went really fast through that. Yes.
True positive and false positive are more similar to the sensitive and specificity.
So true positive is the same thing as the specificity. So let me just pull this back up again. So you could, what's the relationship between false positive, true positive, and sensitivity specificity? Well, true positive is the same thing as sensitivity. Same thing. True positive rate. How many true positives over how many total predicted positives. So how many true positives out of how many total positives? False positive rate is just 1 minus specificity. So here, and you can sort of see that here. I don't know if that helps or not. But, yeah. Any other questions about this? No one went through this really, really fast. Okay.
Yeah, do you mind just going through like one more example, like 0.15? Because I'm just totally not getting that at all.
Sure.
It's like where are you getting those numbers?
So, any particular one?
Try 0.15.
Sure. So, 0.15, everything above 0.15 we're predicting to be spam, sorry. And then under is ham. So, of all of the actual spams, how often are we predicting correctly? 100%. Exactly.
I don't even get that. How do you get that?
So, look at the spam here. That's above 0.15, so that would be predicted as spam. That's 0.6. We would predict that as spam. We would predict this as spam. We would predict this as spam because they're all above 1.15. That cutoff.
It doesn't matter that 0.6
For the true positive, we're only looking at spam. Now, when the actual value is ham, how often is the prediction wrong?
and then that's where you keep your cutoff straight.
So we're predicting this one correctly, this one correctly. This one will be incorrect. That's above 0.15, and this one will also be incorrect because it's above 1.15. So they have 50%. Make sense?
Where do you get the score value?
The score value. Oh, this is the score value, right? This score value is going to be the output of like the logistic regression. Yes, this is the predicted value.
So that's the predicted value.
Yes.
Like TPR.
This is just the predicted value. This is just the predicted value. This is not how many you got right, how many you got wrong, anything like this. This is just the predicted value, the predicted probability of being spam, according to whatever model you chose.
Okay, it doesn't matter what.
Yeah. The ROC curve is something that can be applied to any binary classification problem. It's not specific to the logistic regression. Yes. You can use it on K and N. Yep.
You basically, to evaluate your model, you take the probability values, predict your probabilities, and then you have cutoffs and just
Say it one more time? Yes, exactly. Now, I will say this only is applicable to binary classification problems. But that being said, a lot of problems out there, probably more problems than any other kind of problems that I've seen out there, are binary classification problems. So the ROC curve is used very widely. And I think I might have misspoke earlier. I think there is a lot of value in knowing this. The reason I wouldn't have included is because it is sort of complex. But what I can do is I found a really good video that really just reiterates a lot of what I said, but in a different way. And I'll send that out if you would like to watch this. It's only a 15-minute video. It's really well done, and it reviews a lot of what we said. So if that would be helpful, I can send that out as well. Yes?
Is there a cutoff value for this one that you would suggest? Like, how do you know which cutoff value is best one to use?
That's a good question. As far as I know, there isn't a way to, there isn't like a nice, simple function to get that cutoff value. What you would do is based on the context of your problem and also looking at the, let me see. Yeah, you would probably, what you would probably do is based on the context of your problem, you would choose what threshold value you're looking at, because depending on what problem you have, you may want to minimize your true positive rate versus your, like, they're not equally important, depending on what the problem is.
Illness, you don't want to have any like false positives
If it's in, yeah, so if it's an illness, you'd rather, like, if it's spam, you want to make sure, if it's a spam analogy, you want to make sure you're not incorrectly, labeling something as spam. But if you let something through that is spam, that might be not as big of a deal. Yeah.
I don't know if anyone else would be helped by this, but could you complete that graph that's on like the fourth slide based off of this exercise?
Yes.
Because there's not a complete graph in the slides.
This one?
Yes.
Yeah. I apologize for that. It would basically, it would start over here, like, it's basically these values here. It's these true positive is the y value. This is the y value here. This is the x value. I can put it up on the slide and come back to it at the beginning of next class.
Okay.
Sure. Yeah. Definitely. I mean, it's what it's going to do is it's going to start here, and then it's going to go like that.
And then the area under it between that and the 45-degree line would be the AUC.
Yes.
Okay, so we're
Actually, the area would just be
everything.
It would be everything. It wouldn't just be between 45 degrees.
Okay.
Same thing.
So what would we look for in an AUC?
Good question. So you would want to maximize AOC. Intuition. You want to maximize accuracy. You want to maximize your AOC value.
Okay.
Yeah. So you want to. Another way of saying it would be. Going back to that. When an actual value is spam, how often is the prediction correct? Well, you want that to be high. When an actual value is ham, how often is the prediction wrong? You want that to be low. So you like the intuition would be, some parameter that was over here would be really nice to have. Got a really low false positive rate, really high true positive rate. So if you've got a receiver operating characteristic that's like this, it's going to be a higher area, which corresponds with high, at least some thresholds that are giving you high true positives and low false positives, which is good. Versus one that's closer to like a 45-degree line, which would be less effective. I know there's a lot of complexity in this. So yeah, with that being said, we've got 5 minutes left in class. Let me just go over the homework real quick and get my computer as well. And we will come back to this and we'll talk about, we'll actually go through some examples in the beginning of next class, calculating these classification rates, calculating the false positive rates. We can review this topic, ask any more questions you guys have. I'll send out the video. Watch the video. I strongly encourage. It only takes 13 minutes of your time. Watch the video. Come back and ask questions next class. And yeah, we'll go from there. Go through an example of how to actually calculate this metric in Python. So that being said, homework for this next week is one thing. It is to prepare your project presentation. First project presentation. Your goal here is, I included a link to it here, your goal is a 2 to 3 minute presentation on the data that you've gathered, the initial things that you found in the data, whether that's data cleansing tasks that you've done, data cleansing tasks that still need to be done, exploratory graphs that you've created, exploratory techniques you want to continue in the future, what your target variable is, what your input variable is, why you're interested in this problem in the first place, what are some ideas you have about how you're going to structure the problem. Maybe it's a classification problem. Most of the students in my last class did a classification problem, and they're trying to predict something. So, in your case, what is your response variable? What is the class you're trying to predict? What are the variables you're using to try to predict that? You don't have to present modeling results. We do not expect that at all. We just want to see that you put some thought into it. You have a data set that you're making progress. It doesn't have to be a finalized, pretty tidy data set yet. Just a status on here's what I've done so far, and here's what my plan is for the upcoming weeks. This could be one slide, packing everything on it. It could be a couple of slides with lots of information on it. So the format's not super important. It's just what's more important that you have something visual for us to look at, and you give it to us for just a couple of minutes. Do you guys have any questions about that?
Are we presenting this class? Or is it just
Yes.
Okay.
Presenting. Yes. We'll do that the first thing in class, so make sure you get that pull request in before class. Any questions? All right. Have a good Saturday night and Sunday.